this work is the general question which effective field theories can be consistently completed in a fundamental theory of quantum gravity. And as we just heard, we have to distinguish between, on the one hand, the swampland of seemingly consistent effective field theories, which, however, do not have such a completion to quantum gravity, and, on the other hand, the landscape of fully consistent quantum gravity theories. And the boundary of these two types of theories is the subject of a number of conjectures, which were just beautifully reviewed. These conjectures are of general scope. They do not, in general, use string theoretic arguments, but the downside is that in such cases, they are also not sharply proven, of course. They're conjectures. So string theory offers for us a very convenient opportunity as a framework for quantum gravity to actually test these conjectures explicitly and to make computations where we can check them, where we can quantitatively maybe even develop them further. And on the other hand, this also allows us to learn a lot about string theory, about the geometry behind string compactifications and manifestations of some of these quantum gravity conjectures in string theory. So I will be discussing a subset of the quantum gravity conjectures that we just heard. The no global symmetry conjecture states, as we just learned, that there should not be any global symmetries in quantum gravity, so our natural starting point will be to discuss what goes wrong if we start with the gauge theory in presence of gravity and take the limit where we let the gauge coupling go to zero. According to the completeness conjecture, the full charge letters in a gauge theory should be populated. This is obviously violated in perturbative open string theory, so what goes wrong here, if anything? The weak gravity conjecture was just reviewed, so what is the correct numerical bound for this tower of states that are super extremal and which states obeyed in string theory will be our question. And most importantly, the Swampland distance conjecture predicts an infinite tower of asymptotically light states at infinite distance. And the point will be not only to identify those states, but also to ask what will be the nature of the theory at infinite distance when these states become light. We are going to address these questions in a specific framework, namely in the framework of compactifications of string theory to 6 or 4 dimensions with minimal supersymmetry, so 8 or 4 supercharges. We can think of these, for example, as F-theory compactifications to 6 or 4 dimensions as an example of an open string theory, or equivalently in terms of the heterotic manifestations when a dual exists. And the main message is that, indeed, we can check that whenever we take the limit of a gauge coupling in a gauge theory to 0 while keeping the Planck scale fixed so that gravity remains dynamical, then we find a tower of exponentially light states, which are in fact charged, according to the Swampland distance conjecture. We can verify and prove the weak gravity conjecture in those instances, and identify the relevant tower of states, which in this case are non-BPS. So nothing that I'm going to say will rely on BPS nature because of the amount of supersymmetry we will be discussing. The main message is that this realization of the weak gravity conjecture in string theory, in the context we will be discussing, really relies on a conspirational interplay, so to speak, between Kähler geometry of string compactifications on the one hand, between properties of the string spectrum, modularity of an elliptic genus, and BPS numbers, Kupper-Kummer-Buffer invariance, and properties of black holes. And the general theme of this talk will be that, at least in the corners of string theory I'll be discussing, what lies behind these quantum gravity conjectures is the fact that as we go to asymptotically weak coupling regions, there emerges a tensionless, critical, weakly coupled string. A soliton will become a new fundamental string in a dual frame, which can be either the heterotic string or also a type 2 string. So in this sense, it's really the interplay of course, well-known and standard ideas in string theory, duality and stringiness as such, which underlie the realization of quantum gravity conjectures in the context we'll be discussing. Okay, so let's start with a concrete framework. Compactifications to 6 dimensions first. In the language of F-theory, this means compactification of type 2B with space-time filling 7 branes. The compactification space is a Kähler surface, which we take to be compact so that gravity remains dynamical at all stages. The gauge dynamics is associated with 7 branes which fill space-time and wrap complex curves on this internal space. And there are 2 types of couplings that we need to keep in mind. the Planck scale, and hence the gravitational interaction strength, is set, of course, by the volume of this compact internal space, whereas the inverse gauge coupling is set by the volume of the curves wrapped by the 7 branes. This can be done for any gauge group. For convenience, we will focus mostly on abelian gauge groups, and in this case, this curve C has a beautiful interpretation in arithmetic geometry. It's the height pairing of a rational section. This need not bother us, except for the very last slide of this talk. So just think of it as some curve wrapped by a 7 brane. So given such a setup, what happens if we take the gauge coupling to 0 in a limit while keeping M Planck finite? As we just heard, we expect that this is not possible in a controlled way because no global symmetries should rise, and the general expectation would be that this offensive limit should really be at infinite distance. It should not be reachable in supergravity, and at the microscopic level, the effective theory should break down due to the appearance of light states. And there has been a substantial corpus of related works analyzing these and similar or other ideas in complementary contexts, and I invite you to, in particular, attend Eran Palti's talk tomorrow, and also maybe, if you have time, to look at some of the talks at the String Phenomenology Conference at CERN 2 weeks ago, where this was a major topic. So let's go back to F-theory and first try to see what happens in this pathological limit, and the message will be that we will recover a dual tensionless heterotic string in the limit G-Young-Mills goes to 0. Why is that? So we are interested in the limit where the volume of the compactification space stays finite, while the volume of the curve wrapped by the 7 brane goes to infinity, so that the gauge coupling goes to 0. Now, one can prove rigorously that in such a situation, there must exist another curve, a rational curve C0, which intersects the 7 brane curve, and whose volume goes to 0 in the inverse manner, as the volume of the 7 brane curve goes to infinity. This is intuitively clear if we think of the slogan that when you have a complex surface and you make one direction, say, very big, then obviously the transverse direction, so to speak, needs to become correspondingly small. This, of course, is just a cartoon. This fact can be proven in Kähler geometry, and in particular, with the help of Maurice-Kohn theorem, we can prove that indeed there exists such a curve, C0, which becomes correspondingly small at this rate, which is a rational curve and which squares to 0, so it has trivial normal bundle. Why is this important? First of all, one can explicitly check now that this limit indeed lies at infinite distance in moduli space. This is easy to see. One has to look at the metric of tensor multiplets in 6 dimensions which govern this motion in moduli space, and one finds indeed this relation between the distance and the parameter t, which we take to infinity, which is 1 over G-Young-Mills squared. And the second, more interesting statement would be that there should now appear infinitely many charged states, massless, at an exponential rate in this limit. So the first thing that would come to mind is you might think that there should now arise particles from wrapped branes. However, we are in type 2b theory, so we cannot wrap a 2 brane on a curve because there is no such thing. But we can wrap a 3 brane on this curve. This gives rise to a string. However, just a single string. We don't get infinitely many strings. We get just a single string because this rational curve can be wrapped only once. But nonetheless, we get a solid tonic string in 6 dimensions whose tension is governed by this volume of this curve C0, which goes to 0 exponentially. So now to get infinitely many states, the clear idea is to think of the excitations of this asymptotically tensionless string. And this indeed is the correct answer, because this string is not just any non-critical string, but it is a very special string. It is a critical heterotic string. So in this limit, we get a heterotic string, which becomes asymptotically tensionless and asymptotically weakly coupled. This can be guessed already by going to the M-theory picture, where the elliptic vibration over this curve is a K3, which is well known once wrapped by an M5 brane in M-theory to give rise to a critical heterotic string. One can also do the same analysis directly in F-theory. It's a little bit more complicated, but the result is the same, that the string has the correct zero-mount content to identify it with a heterotic string. In particular, at the intersection of the string and the 7 brane, there arise 16 left-moving zero modes, which are charged under the gauge group of the 7 brane, and which therefore give rise to a flavor symmetry, flavor current in the left-moving sector of the string that is to be identified with the gauge symmetry. So this string, this heterotic string, becomes weakly coupled as it becomes tensionless. One can show this directly in supergravity, or also by invoking duality with the heterotic string, even though this is not necessary. In fact, just as background information, these compactification spaces for which we can take the limit Young-Mills to 0 as described fall into two classes. One can prove this. Either they are rational fibrations, so they are Hirzebruch surfaces, so there is a P1 fibered over a curve in the base, and in this case, this P1 fiber is the curve whose volume goes to 0. And in such a case, it is well known that a D3 brane wrapping this curve is the heterotic string, and its string coupling goes to 0 in the limit of vanishing curves to 0. More generally, these curves can be, these surfaces can be blow-ups of such spaces by including extra rational curves. In this case, on the heterotic side, we are not in a perturbative regime. We have extra NS5 branes, but our analysis is still valid in these situations because away from the NS5 branes, the string is still weakly coupled, and this is the situation that we call quasi-perturbative. Okay, so we've seen that we have a weakly coupled or quasi-perturbative heterotic string in this limit Young-Mills goes to 0. So we would now like to prove the weak gravity conjecture for the excitations of this heterotic string. There have been previous results closely related to this in the literature. For example, it has been pointed out that spectral flow implies the weak gravity conjecture for the perturbative heterotic string, and that this in particular can be used to prove the sublattice weak gravity conjecture, for example, explicitly in toroidal models and toroidal orbifolds. The new results of this talk will be to go beyond toroidal situations, so we're in general situations in 6 or 4 dimensions. We will explicitly determine the sublattice of states satisfying the weak gravity conjecture and explicitly match with the black hole solutions. So what lies behind this analysis technically is to consider the elliptic genus of this heterotic string that emerges. The elliptic genus is well known to be an index that counts excitations in the subsector of the string with Ramon boundary conditions on when we take the string world sheet to be the torus. In particular, we include a fugacity for the flavor U1 symmetry in the left-moving sector. Recall that this is the same as the gauge symmetry in the space-time by the argument I gave. Hence, in this way, we get information about the degeneracies of a subsector of string excitations for this dual heterotic string. And we get information about the states at given left-moving excitation level n and given U1 R charge. Hence, if we have this information, we can check explicitly if the weak gravity conjecture is satisfied or not. In fact, a great deal of information can be read off already from the well-known modular properties of this elliptic genus, or of the subsector of the partition function. Namely, it has been well known that in a perturbative sector, the elliptic genus is just a ratio of modular forms of certain weight and a certain so-called fugacity index M. The fugacity index tells us how the elliptic genus transforms under such generalized SL to Z transformations. This fugacity index M is of crucial importance for us. It will determine the coarseness of the sublattice of states satisfying the sublattice weak gravity conjecture. It can be read off from the Toft anomalies on the world sheets with respect to the flavor symmetry on the U1, which corresponds to the gauge symmetry. And in our context, it is given by an intersection product of the two curves wrapped by the 7 brane and the D3 brane, which gives rise to the string, respectively. So we have explicit control over this sublattice, coarseness. All of this is in the perturbative regime. However, it's important to stress that most generally, our heterotic duals will be non-perturbative. They include 5 branes. In this situation, the elliptic genus will turn out to be only quasi-modular. So it includes also the second Eisenstein series in its generating set for the X space. So the last step is to note that the elliptic genus is just a ratio of such modular forms in order to account for the left-moving vacuum energy. This is of not such great importance. So from now on, we can focus on the numerator, which is a Jacobi form of certain weight and fugacity index, either, in other words, a modular form of the type just presented. And now comes the most important slide, or the most important argument. Every such weak Jacobi form is well known to allow for a theta function expansion. It can be written in terms of a sum like this, where the theta functions are given explicitly here, and these HL are certain vector-valued modular forms. Now consider the subsector L equal to 0. This subsector is always there because this is where the left-moving tachyon lives. By inspection, we see that it contains a sublattice of states of charge 2mk, where m was the fugacity index, whose corresponding left-moving excitation level is given in this form. So in other words, we always have a particular distinguished sublattice of states, sublattice of coarseness 2m, satisfying this relation. And the claim is that these are the states satisfying the sublattice weak gravity conjecture. This fact, before I come to this, can actually be checked explicitly. If we want to explicitly evaluate the elliptic genus, we make use of the fact that this index of 60 string excitations is beautifully related to Gopa-Kumar-Waffa invariance of 5-dimensional BPS states. This is because F theory in 6 dimension on a circle is M theory in 5 dimensions. If we wrap the string on the circle, we get a particle, a BPS particle in 5 dimensions, and the BPS invariants counting those are the same as the elliptic genus invariance arising in F theory. So using mirror symmetry, one can evaluate this for various examples in a closed form expression, and one can check that indeed one finds this sublattice of states which satisfy a particular charge to left excitation relation. So now let's come to the weak gravity conjecture. The original argument was that charged black holes should be able to decay, so there should exist super-extremal states, which are super-extremal with respect to extremal black holes. So clearly we must ask which are the relevant super-extremal black holes to compare to. We are working in the limit where G-Young-Mills goes to 0, and in that limit it turns out that the relevant black holes are the dilatonic Reisner-Nordström black holes. This is because we have essentially just one modulus left, namely the modulus that took us to infinite distance to G-Young-Mills equal to 0. This modulus controls the gauge coupling of the U1, and hence the black holes to consider are really the ones that are associated with the dilatonic Reisner-Nordström, with the dilatonic Einstein-Maxwell Lagrangian. The charge-to-mass ratio for those black holes has been computed in the literature. There are two important contributions. One comes purely from the gravitational part, and another contribution comes from the fact that also the dilaton now has a profile. In the present situation, this prefactor alpha can be computed to be universally equal to 1 in 6 dimensions. This is true in all these 6-dimensional 1,0 theories. So the correct bound is indeed q squared, g squared has to be bigger m squared for the particle. And this has also a beautiful interpretation in terms of a scalar weak gravity conjecture, as discussed first by Eran Palti, and as we will maybe hear more about tomorrow. So the now that we have established which bound to consider, namely this bound, we can compare to the sublattice of particles that we found, and this is now a simple exercise to translate the left-moving excitation level into the mass using the the usual formulae. It's important that we are working in the weak coupling limit, where we can actually trust the relation between excitations and mass, as in perturbative string theory. Plugging everything in, we find that indeed the sublattice of states that we identified based on modular properties of the elliptic genus lies above the blue curve associated with the black hole. So we indeed find a sublattice of super-extremal particles, where the sublattice is given geometrically by this intersection product in the theory. Now, if we knew what the value of this were, we would know what the maximal coarseness of the lattice is. There are some conjectures on this, but this refers now back to some deep properties of the properties of these curves here, and I'll be happy to comment more on this if you're interested. This was so far in 6 dimensions. Now, the generalization of this, or the extension of this to 4 dimensions with n equal 1 supersymmetry is substantially more involved, because the geometry is more involved and also the elliptic genus is more involved. For reasons of time, I will be very brief. Let me just point out that the elliptic genus now depends in particular on the flux of the compactification. It is well defined, or non-zero only in chiral theories. And for certain types of fluxes, one finds situations where the elliptic genus only contains manifestly shifted sublattice of super-extremal particles. This is because in 4 dimensions, the weight of the elliptic genus is -1, so it's antisymmetric in exchange of the fugacities. So we find cancellations here, but we nonetheless, by a theta function decomposition argument, can still find a shifted sublattice of this type with L bigger or equal to 1, that satisfies the weak gravity conjecture. So as a result, the tower version of the weak gravity conjecture is still satisfied. One finds not just a single state or a finite number of super-extremal states, but really a tower of states which become light and which satisfy the weak gravity conjecture. But of course the question is if this is a counterexample or not against the lattice weak gravity conjecture, or we can say that those particles are not manifest in the elliptic genus, which is an index, and of course it may be that the missing sublattice is present in the full partition function, but this is hard to say in such general frameworks. Okay, so the main theme of this derivation has been the emergence of a dual, tensionless, critical, in this case heterotic string at infinite distance, whose excitations give rise to the tower of light particles that we sought for. This, however, is just a special case of a more general situation. We can also look at different situations, different types of compactifications, where we find that as we go to infinite distance in field space, at recoupling now, for example, for some of the 2 forms in the theory, some solitonic strings take over the role of the fundamental string in a dual framework. So this idea of having emergent strings at infinite distances is more general, and there's more work on this to come. In the last 2 minutes, I'd like to switch topic a little bit. Namely, I'd like to address a different question in the context of the Swampland. Namely, can we tell just from the gauge symmetry or the matter content of a supergravity theory whether or not it can be coupled to quantum gravity, to the quantum theory? Or in other words, can we decide if an anomaly-free supergravity theory can be the low-energy effective theory of a consistent quantum gravity theory? This question is particularly well posed in 6 dimensions, where, due to chirality, anomaly constraints are very powerful, and it might come even more than as a surprise that there do exist anomaly-free families of supergravity theories with, say, infinite rank gauge groups, outrageous objects, which cannot be ruled out just based on absence of anomalies at low energies. However, as was pointed out recently in this paper, we have to take into account not only the anomaly considerations of point particles, but also take into account the sector of BPS strings which may exist, and in fact in this case does exist in the supergravity, namely requiring that such BPS strings in the supergravity theory be well-defined and consistent, leads to bounds on the gauge content of the supergravity theory and allows us to rule out a number of these seemingly outrageous theories. What remains mysterious even after this analysis, however, is again the abelian gauge sector. In particular, there is a candidate for a potential Swampland, a family of 6-dimensional supergravities with infinitely many U1 gauge groups, which would clearly be counter to the general idea that there should only be a finite number of light fields. As it turns out, the very strings that we discussed in the first part of this talk solve this problem, namely demanding unitarity in a 60 supergravity analysis alone for the supergravity analog of those strings allows us to rule out infinitely many abelian gauge group factors and to place a bound on the number of abelian gauge groups in such supergravities under certain assumptions that I'll be happy to specify. And this result is particularly interesting in the context of F-theory, and now I cannot spare you some of the F-theory details. As has been very well known, abelian gauge groups in F-theory correspond to a beautiful object in arithmetic geometry, namely rational sections of elliptic vibrations, and the number of such U1s corresponds therefore to the rank of this group of rational sections, the model Y group. Now, it's been a long-standing problem in mathematics what the model Y groups say of elliptic Calabi-Yau threefolds is. And by applying these Swampland bounds to the heterotic string that we just discussed in F-theory, one can show, in fact, that the number of such abelian gauge group factors must be always smaller than 16. So in other words, one can use this as a physics proof of a new math theorem that the rank of the model Y group cannot be bigger than 16. So we are quite happy that after all what that mathematics gave to us in the Swampland context, we can now give something back to mathematics, and it will be interesting to see if this bound can be proven rigorously on the mathematics side. And with this, I'd like to conclude and thank you for your attention.
Thank you very much, Timo, for this nice talk. We have time for questions. Comments as well.
So, can you come close to saturating the 16 at the end?
Very good. So the current record is 10. This is on an elliptic vibration over P2 by Noam Elkies. He's been trying very hard to push it. Nobody has gone higher, and it's not known how to do this. And of course, if I may add, clearly the much more interesting question, of course, mathematically would be what the model Y group of an elliptic curve as such would be. Unfortunately, we cannot say anything about that because there is no corresponding F-theory associated with this.
So if not, we thank Timo again. And Mark wants to make one or two announcements.
Okay. Thank you. Yeah, I'd like to make two announcements. One is about the photograph. The photograph will be taken before lunch at the end of the next session. It will be taken in this room. Please don't leave the room. And the other is about the visual